So in 6.4, we're going to work with logarithmic functions. Remember, in math, we have this inverse operations. So we have this inverse thinking, if you will. So if we have addition, then the inverse of addition is subtraction. If we have multiplication, the inverse of multiplication is going to be division. Then when it comes to powers, like squaring, so a lot of times they'll do squaring with x to the power 2. And then the inverse of squaring is going to be the square root of x, if you will. So if you have squaring, you have a power 2, and then inverse is going to be this square root symbol. So this is where we start to get into some strange symbols, which we call radicals. So if I have like cubing, in other words, if I raise something to the third power, the inverse raises something to the third power is to take the cube root of that value. So I have this inverse thinking. This also carries over into what we call inverse functions. So what we're getting into now is what's called the logarithmic function, which is going to be the inverse of a exponential function. So remember, if I give you y equals a to the x, that's the exponential function. Now, if I want to find its inverse, what you have to do is switch the rows of x and y. So x is equal to a to the y. Now, to solve for y, though, there's no way to solve this for y. So this is where we have a logarithm that comes into play that says y equals the log of a, the log of x, I should say, base a. So the log of x base a. So notice that in a logarithmic function, the exponent goes on one side of the equation by itself. The number or the expression that was raised to the exponent becomes the base of the logarithm. So this becomes what we call a little subscript. And then the x becomes our domain. So domain and y is still the range. So we have input values, output values here. So as we move forward, a logarithmic function with the base a, where a is greater than 0, again, a cannot equal 1, is denoted with y equals the log of x base a. They say this reads as y is the logarithm with base a of x. So I kind of read it a little bit differently. So I read it as y equals the log of x base a. So we have y equals the log of x base a. This is a logarithmic expression. This is only true if and only if a is equal to a to the y, x equals a to the y. So notice how I had that kind of going on over here as well. The domain of a logarithmic function is going to be y is equal to the log of x base a, where x is greater than 0. So you cannot take the log of a negative value. So remember, we had a range restriction with an exponential function, but since the inverse of an exponential is a logarithm, the range restriction now becomes a domain restriction in the logarithm. So that's where we'll talk more about this as we go on. So anyhow, we want to change the exponential statement to an equivalent logarithmic statement. So the way this works is, since this is an exponential statement, we want to change it back into a logarithmic statement. So notice that the y is the exponent. So the 3 comes down on one side by itself, and that's going to equal then, it's going to be a to the y. So notice how this, we have 7 is the, actually, this is the a. Notice that that becomes the little subscript of the logarithm. That means the 343 is what we end up taking the log of. So the log of 343 base a. I'm sorry, not base a, but base 7, since a is actually a 7 there. So the key thing to pick up on in changing an exponential form into a logarithmic form is the exponent comes over to one side of the equation. The base is going to be the subscript of the logarithm, And then the remaining piece becomes what we take the log of. So the log of 343 base 7 is going to equal then this 3. That's how that is going to look.